Okay, so maybe we can already start. So I'm very happy to introduce Johan. Are you ready, Johan?
Yeah, I am.
Nice. Yes, I'm happy to introduce Johan Kommelin from Utrecht University, and he's going to tell us a bit about aspects of the liquid tensor experiment. Yeah.
Okay, yeah. Thanks a lot for the invitation and for showing up. So yeah, I want to tell you a bit about this liquid tensor experiment. So the plan for today, the liquid tensor experiment, there are sort of two components. One of it is computer verified proofs. And so I want to say something about that, mainly just give a demonstration of what this looks like. And then there's condensed mathematics. And so I want to sort of try to give an idea of what the condensed mathematics in the liquid tensor experiment is about. And yeah, try to give an overview within the time that this talk allows for. So let's get started. So first of all, I want to start with a Lean demo. So Lean is a computer program that is sort of like a programming language, but it is a special kind of programming language that has support for or is expressive enough to not just write down functions that a computer will be computing, but it can also write down mathematical definitions and theorems and proofs. And it then has support for checking these proofs to show that they really are logically correct proofs. So let's see what this looks like in practice. So I guess, so now you see a code editor, I guess?
Yes. Yeah.
Okay, great. Right, so this is a text editor, similar to the kind of text editor that you might use to write LaTeX. And we're going to write down some mathematics in here. So I suggest we start with writing down a theorem statement. And I'm going to write down a very classical result that might have won Euclid a Fields Medal if that existed a few thousand years ago. So we're giving ourselves a natural number n, and we write this down with this funny symbol colon instead of the element of symbol, but basically that's just a bit of notation. And now that we have this natural number n, we're going to make a claim. We're going to say there exists a p greater than n such that p is prime. And so what this is saying is that there are infinitely many prime numbers. Okay. Then we write down colon equals, and now we have to give a proof. And so Lean is complaining. It says unexpected end of input because it's expecting a proof and we didn't give a proof. And so we write down by to say, well, we're going to prove this by the following steps. But now we're a bit stuck. It's again complaining, unexpected end of input, etc., etc. And we don't really have a very good idea of how to proceed with these proofs, maybe. But Lean has a magic feature that allows you to look inside its brain. And so I'm going to click this symbol for all and ask it to toggle the info view. And now a second window appears. And in this second window, we have this so-called tactic state on the right-hand side. And it tells us, okay, we have one goal, which is what comes after this funny sideways t. It says you have to show that there exists a p greater than n such that p is prime. And we have the yellow things are going to be the assumptions. So we have a natural number n as an assumption. And okay, this didn't help too much yet, but at least we sort of have a reminder of what we need to do. And now you need to know a little bit of Lean in order to continue. But so I'm going to say let capital N be equal to little n factorial plus 1. And as you can see, now we got a new entry in the list of yellow things, namely capital N, which is defined to be n factorial plus 1. Okay. And now I'm going to say, well, let P be the minimal factor of capital N. And this gives us another extra entry in the list of yellow things. And now I want to say, well, this P that we just constructed, this is going to be our witness for the claim of the existential quantifier that there exists a P such that blah, blah, blah. So I'm going to say use P. And now we see that the goal changed. It's also highlighted in green. So if I move my cursor in the left window before the use P, we see there was an existential. There exists a P such that. And now we tell it to use the P that we constructed. And it says, okay, so we're going to use that P. And for that P, you have to prove that P is greater than N and that P is prime. And I mean, these letters are just names. So for example, we could have called this Q. Let Q be the minimal factor. And then use P doesn't make sense because it doesn't know about any P, but we can say use Q. And then now, of course, we need to prove that Q is greater than N and that Q is prime. But let's just call it P again, because, well, primes are always called P. Okay, now we need to do two things. We need to show that P is greater than N and that P is prime. And because I've given this demonstration several times before, I know that it's a good idea, a useful idea to first prove that P is prime. So we're going to make a claim for like a little sublemma or a subclaim in this proof. We're going to say have P is prime. And in fact, because we want to refer back to this claim, we're going to give it a little LaTeX label. And I'm going to call it HP because this is the hypothesis about P. Okay. And the effect of this line is that now we have two goals, as you can see in this tactic state. We have two goals. First of all, we have the case HP, which is this little LaTeX label saying we're going to prove that P is prime, given our current assumptions. And then in the main goal, we now have a new yellow entry in our list of assumptions that P is prime, because we've justified that in the subclaim. And we can use that to prove our original goal that P is greater than N and that P is prime. Okay. So now we have two goals. We write this little bullet point to focus on the first goal. So now that I wrote that bullet point, we only see the goal of the subclaim. And I'm just going to write sorry, because I don't want to be bothered with proving this. And it says, okay, no goals. Of course, no goals only means no goals within this subclaim. Whenever I move to the next line, I get my original goal back. So there's still one goal left. We now know that P is prime, and we have to prove our original goal. So just to structure the proof, I'm going to make another claim that P is greater than N. I'm also going to prove that using sorry. And now we have these two assumptions in our list of yellow things. And so now it should be easy. And we say, well, this is now a tautology. And now it really says no goals. So we've finished all the goals. There are no goals left. And we finished the proof of this theorem. Except that there is this orange squiggly line under the word Euclid. And in this pop-up, it says declaration uses sorry. So Lean remembers that we cheated, that we used sorry. And so actually this proof is not a complete proof, as we all expect. So that's good. So let's go back and fill in these sorries. So here's the first one. We want to prove that P is prime. Well, P is by definition the minimal factor of capital N. So you might guess, well, there's probably a lemma about the minimal factor of a number being prime. So this indeed exists. So we're going to apply that lemma, apply minimal factor prime. Okay. And now we see that we're not done with after this lemma, because there is a side condition. If we hover over minimal factor, over here, if we hover over the definition of minimal factor, it says it returns the smallest prime factor of n for n unequal to 1, because of course 1 doesn't have a prime factor. So now we still need to show that capital N is not equal to 1. Okay, well, why is that? Capital N is n factorial plus 1, and factorials are always positive. So let's remind Lean of this fact. We say, observe that factorials are always positive. And now we should be done. Okay, maybe we don't really know how to tell Lean that this is now obvious. So we ask it for a hint. And Lean says, well, I have a little program that is able to construct simple proofs about inequalities and equalities and things like that. It's called linear arithmetic. Okay, so we click on that suggestion, and now the little linearith program says, okay, I can take this assumption that factorials are positive and use it to prove that n is not equal to 1. So then we don't have to bother with the simple manipulations of, well, add 1 on both sides, then you still have an inequality, and then you can use that to show that n is not equal to 1. Good. So that finished the subclaim that P is prime. And now we have the other subclaim that P is greater than n. And so at some point in this proof, you typically have to do some reasoning by contradiction. And this is the point where we do that. So we're going to say, by contradiction, assume that P is at most n. Okay, so the result of that is that now we assume that P is at most n, and we have to prove a contradiction. So we have to prove false. And then we say, well, how are we going to prove false? Well, we know that P is going to divide capital N because it's the minimal factor. We know that P divides n factorial because P is less than n. And so P is going to divide the difference between the two, which is 1. But of course, primes don't divide 1. So let's do that. So we say, let's start with the observation that P does not divide 1. Okay? And then we say, well, now it suffices to show that P divides 1 by contradiction. And so what we're left with is showing that P divides 1. And then we say, okay, well, observe that P divides capital N. And maybe we have to give this a name because we will refer back to it. So observe this, observe that, P divides n factorial. And so Lean is thinking a bit. You can see these orange bars. So now they're gone. It's happy. We have these extra assumptions in our list of yellow things. And now we should be done. So now we ask it, well, what exactly do we need to finish this? And there will be a little lemma in the library that says, well, if you divide A and you divide A plus 1, or if you divide A and you divide A plus B, then you also divide B. And for some reason, my laptop is a bit slow. I guess there's some other program running in the background. I expected it to be finished 10 seconds ago. Let's see. Ah, there you go. Okay, so it found a little lemma in the library. We click on it, and now it's happy. So it says there are no goals to be solved. We can remove that line. Okay, and now it should be, now it's completely happy. There's no orange squiggly line. Oh, sorry, there's no orange squiggly line anymore under Euclid. And so it checked the entire proof, and it agrees with us that for every natural number, there is a prime number that is larger than n. So this was the short demonstration that I wanted to give of how it looks like to work with such a program, and how you sort of have this look inside the brain of Lean, giving you an overview of exactly what the assumptions are and what you need to prove, and how Lean gives you feedback by complaining if certain steps in the proof are not complete. Right, so I'm happy to answer questions about Lean right now. We can also leave this till the end, but maybe someone has a question at the moment. Okay, so let's move on. Let me move a little Zoom thing out of the way. Okay, so yeah, if you're interested in knowing a little bit more, I mean, I can also share these links at the end of the talk again, but this is a website that contains a lot of information about Lean. If you want to play with it, how to install it, tutorials, how to get started, etc., etc. We also have a chat room where lots of mathematicians hang out that are working with Lean, working on projects. And finally, this is a website hosted in, come on, where is this? Somewhere in Germany. I forgot for a moment. And it contains an online Lean environment. So it allows you to play with Lean. There's a specific setup where you can prove that the natural numbers are like have commutative addition, commutative multiplication, etc. So very easy stuff on the math side, but it's a tutorial that walks you through the basic way of how to use Lean. Yeah, so that's a very easy way to get started without needing to install anything, etc. So that's roughly what I wanted to say about computer verified proofs in this talk. But yeah, I'm happy to answer any kind of questions about it now or at the end of the talk. So if there are no questions now, then I'll move on to the next section, which is about the condensed mathematics and the theorem that we checked in Lean about it. So what is the motivation for that? The motivation for condensed mathematics maybe comes from my point of view, in a large part from wanting to mix algebra and topology. So, of course, there's algebraic topology. That's not what I'm talking about. I'm talking about topological algebra, right? We have group theory, we have the ring theory, but then we also have theorems about topological abelian groups or about topological rings. The real numbers are a field and they carry a topology. We also have the p-adic numbers, etc., etc. And the point is, when you mix algebra and topology in these ways, several really nice results from algebra stop working. So there are two problems, maybe. First of all, the isomorphism theorem fails. And the very easy example is if you take the real numbers, and on the one side you put the discrete topology, and on the other side you put R with its usual Euclidean topology, then this function is a bijection, but it's not an isomorphism because the inverse is not continuous. So you expect this to have maybe a trivial kernel, but a non-trivial co-kernel. but that's not true. So this means that the category of topological abelian groups is not an abelian category. And the other point is that the whole theory of tensor products basically breaks down, or at least becomes incredibly hard. So Grothendieck, in his thesis, defined many different kinds of tensor products of topological vector spaces. And basically, after that, he left functional analysis and decided, I'll just work on algebra, algebraic geometry instead, and revolutionize that field. And yeah, in a sort of ironic twist of history, one of the inventors of, or basically the two inventors of condensed mathematics are going the other direction. They started working out in algebra, and now they're sort of also venturing into functional analysis, exactly tackling this point of topological tensor products being really hard. So we'll get back to that in a moment. So what now? Well, one of the philosophical reasons for why mixing in topology with algebra is not so well behaved is that in the definition of a topology, you're really talking about sets of subsets, which is a second order notion. It's not really a first order notion. Algebra interacts really well with first order concepts, but second order concepts, not so much. So that's somehow a complaint, a constraint or a problem. And so Clausen and Schulze basically decided, well, if the definition of a topological space is the problem, then somehow we should try to fix that. And okay, so why do I care about getting this fix in place? So these are some personal motivations. One really cool result rolling out of this whole framework of condensed mathematics is that it unlocks a unified category of geometric objects. So once you're able to mix topology and algebra in a way that also has good categorical properties, you can run the whole machinery of the way we do in algebraic geometry. You have a commutative ring, you take its prime spectrum, that gives you an affine scheme, then you glue together affine schemes, this gives you schemes. And you want to be able to do the same thing in other places, and that's also what people do or have tried to do. Like with adic spaces, you start with some sort of topological ring over the p-adic numbers, maybe. Let's say, technically they're called Huber rings or Huber pairs. And you define an adic spectrum of those, and you explain how to glue them. And so within condensed mathematics, there will be a notion of a so-called analytic ring. And these analytic rings have an analytic spectrum, and you can explain how to glue them. And so that gives you geometric objects. And those geometric objects generalize manifolds and schemes and adic spaces, because these analytic rings generalize discrete rings if you just, well, don't really say anything about the analytic side of the story. But they also generalize all sorts of p-adic rings, and also all sorts of rings showing up in real and complex geometries, like rings of holomorphic functions on a disk or things like that. And so by having one unified category of rings that generalize all those rings showing up in various kinds of geometry, you can then imagine that you can also build a unified category of geometric objects. And so it allows to mix functional analysis and homological algebra by coming up with well-behaved tensor products and categories of objects that, again, generalize the objects that show up in functional analysis, like Banach spaces, Frechet spaces, etc., etc. And these new categories will be abelian categories with really nice properties. So once you have an abelian category, then you can start playing the game of homological algebra. And so that toolkit now applies to those categories of functional analytic objects. And finally, a sort of technical point maybe, but I think it's quite important, is in algebraic geometry, when working with schemes and varieties, we use the category of quasi-coherent sheaves quite a bit. And the whole six-functor formalism of pushing and pulling and right, push forwards, pullbacks, etc., of quasi-coherent sheaves. But this was not available in the context of complex analytic geometry. There's a notion of coherent sheaf, but quasi-coherent sheaf didn't exist because you need to deal with infinite dimensional objects in a controlled way. And that just wasn't available. Because, yeah, there wasn't a flexible enough formalism of taking completions that would be compatible with the whole push forward and pullback notions, etc. Right. So these are reasons why you might want to be interested in condensed mathematics and the theory built on top of it. So what exactly are we talking about? Well, let's start with a very basic example, and let's think about convergent sequences. So we define n infinity, which is the one-point compactification of n. And so we can picture it as follows. So we have the number 0, and then a bit further away 1, and then a bit further away 2, and then closer and closer together we get 3, 4, 5, etc. up to infinity. And whenever we have a continuous function from n infinity to, let's say, a metric space X, then this is exactly a convergent sequence together with some limit point. I guess if X is a metric space, then actually the limit point will be unique. So, but if X is a bit more general and for example, somehow, let's say not Hausdorff, then the limit point doesn't exactly have to be unique. But what I want to point out is that n infinity classifies convergent sequences together with the limit point. And so if X is actually a metric space or at least metrizable, then X is completely determined by its set of points and the set of convergent sequences. Well, okay. And some extra data, namely, whenever you have a convergent sequence or an element of this set of convergent sequences, then you want to be able to know, like, what was the kth term in the sequence and what was the limit point, etc. So you also need to remember all these maps from the set of convergent sequences to the set of points that send a convergent sequence to its limit point or to its first term in the sequence, etc. But once you have all this data, then you can recover X together with its metrizable topology. And this is much more a first order flavor kind of data, because we're just talking about a set of points and not about a set of subsets of those points. And we just have another set which plays the role of the set of convergent sequences. And then we have this other data of selecting terms from those sequences. So that's hinting at a way how we can get a more first order kind of approach to at least metrizable spaces. So condensed sets, at least in their latest incarnation, consist of the following data. So we have, again, a set of points and a set of convergent sequences. But now we want to remember a bit more. So let's say we also want to sort of have a set of convergent squares, like sequences in two directions. And actually, more generally, we just want to remember a set x of s for any continuous quotient s of the Cantor set. So, I mean, I'll show a picture of the Cantor set on the next slide, but I guess it's this crazy fractal-like thing that, if you think a bit about it, it's sort of a very generalized version of this n infinity. And then we also need to know how all these sets interact. So now we want maps from xt to xs for every map from s to t. And every map from s to t, I mean as like a continuous function. So it should respect the topology that S and T get as being quotient spaces of the Cantor set. And then all this data must satisfy some conditions, which turn out to be some sort of sheaf conditions. And I'm not really going to talk about those sheaf conditions, but yeah, you can imagine what they might be. Okay, so here's this picture of the Cantor set, and you can sort of start guessing how things like n infinity are specializations of this, so quotients in a suitable sense. Good. So now we have these condensed sets, and we claim they're very much modeled maybe on this idea of metrizable spaces, but we wanted to generalize topology. So if X is a topological space, can we somehow turn it into a condensed set? And the answer is yes. So we have to give this data for every continuous quotient of the Cantor set. And we just take it to be the set of continuous functions from S to X. And the claim is that if you do this for every continuous quotient, then you get the collection of data that we needed in the definition, and it had to satisfy these sheaf conditions. I claim that works, but I'm not going to say anything about it. And now you wonder, okay, but did we lose any information by doing this construction, by passing from this topological space to the associated condensed set? And in some cases you do, in most cases you don't. So for reasonable spaces, this construction is fully faithful. And with reasonable spaces, I mean things like manifolds, Banach spaces, the p-adic numbers, p-adic integers, etc. So stuff that shows up in differential geometry, functional analysis, and number theory, etc. But if you start with a topological space underlying a scheme, so something that is non-Hausdorff, or you start with something that has a tremendously large cardinality, then the construction will not be fully faithful. But on the other hand, maybe we don't care about spaces that are crazy large, and maybe things like non-Hausdorff spaces, like the sober spaces that underlie schemes, it's maybe a bit of a coincidence that we use topological spaces for that. And we might want to sort of disentangle those two uses of topological spaces anyway. The topological spaces that show up in like for Banach spaces, etc. So all these Hausdorff spaces that really have a nice geometric flavor to them, and then the spaces underlying schemes, it's really the scheme in total that behaves like a nice geometric object, but just the underlying topological space. Well, we could also use something like a locale or some sort of set with the specialization order to model that. Anyway, so maybe we don't care too much. What I want to say is those are not the spaces that we would want to consider as condensed sets anyway. in particular, we don't really mix those with algebra. If you take a group scheme, then the underlying topological space of a group scheme is not a topological group, because, I mean, the underlying space is not even a group, because the product topology on schemes doesn't, well, I mean, the topology on the underlying space of a product of schemes is not the product topology. Anyways, so that was a long-winded way of saying, for all spaces that we care about, this construction is fully faithful. And now the isomorphism theorem works. So if we apply this construction to the real numbers, then we get some condensed set, and we can apply it to the real numbers with a discrete topology, and we get another discrete condensed set. And there is a natural morphism between them. It doesn't have, so the kernel is trivial, so this map is injective as expected. And now it has a non-trivial co-kernel. And this co-kernel, if we call it Q, well, it's a condensed set. So it means that in particular, it comes with this set of points, Q of star. And Q of star will still be 0. So that will still, that's sort of the bit of the condensed co-kernel that we already saw in the initial picture. But now there is also Q of S for all sorts of other continuous quotients of the Cantor set. And Q of S in general looks like the space of continuous functions from S to R modulo the subspace of locally constant functions from S to R. And so whenever S is non-trivial in the sense of, let's say, infinite, then this subspace is a proper subspace, and so the Q of S will be non-zero. And so there is really some gadget now measuring the fact that this map from R disk to R is not surjective. And Q of S, of course, or I mean, this co-kernel Q very much is a new object. It's a condensed set that didn't come from a topological space. So it's, in some sense, it maybe behaves pathological, but on the other hand, it's a new object that ensures that the category has much better categorical properties. And I think it's the kind of leap that was also made when, for example, Grothendieck said, well, we shouldn't just be looking at maximal ideals and varieties. We should really consider all prime ideals, even though they don't give closed points. And we shouldn't just be looking at reduced rings over fields. We should be considering all rings, even rings that contain nilpotent elements, etc., because these nilpotent elements actually measure interesting behavior. And so here again, Q doesn't behave in the classical way like a topological space. It's a new kind of object, but it's an object with useful properties, certainly from a categorical point of view. Okay, so now let's talk a bit about analytic rings. So let's start with a bit of motivation. So products in geometry, under this duality between geometry and algebra, this contravariant duality between geometry and algebra, products correspond to coproducts, and coproducts in algebra are typically tensor products. And so this works really well in algebraic geometry, in the world of affine schemes and commutative rings. But it breaks down in the classical approaches to in the classical approaches to analytic geometry. So in many cases there isn't really a good tensor product to make this duality work. And also, condensed mathematics doesn't solve it immediately. So once we have condensed sets, we can look at condensed abelian groups. These are going to be abelian group objects in the category of condensed sets, or if you want, like a sheaf of abelian groups on this category of quotients of the Cantor set. But, and so this is going to be an abelian category, and it's going to come with a tensor product. It's going to be adjoint, the adjoint functor to the Helm functor. But it's too algebraic because it's just like the tensor product of sheaves that we know. So it's basically a pointwise tensor product, and then you sheafify. And so that's not good. It works for schemes, but not for manifolds. As soon as you seriously start mixing in topology on the coefficients, you get stuck. And functional analysis for a long time has known the answer, except that like there were many answers. So the point is you have to complete your tensor products. So we need a notion of completion. And that's what analytic rings are all about. They give you a way to take modules over your ring and complete them. So the definition is that an analytic ring consists of a condensed ring, R triangle, and then inside the category of R triangle modules, there will be a subcollection of R modules. So there's really this important distinction between R triangle and R, and sort of as a ring, they're the same, but they're really, the way they differ is what is considered a module over the ring. So modules over R triangle are just condensed sets that come with a module structure over this condensed ring R triangle. And a condensed an R module is just going to be whatever this analytic ring thinks its modules are. It's going to be a subcollection of the category of R triangle modules. And we think of those modules, the R modules, as the complete ones. But of course, it can't be just any collection. It must be a well-behaved subcategory. So first of all, it must contain the ring itself. Then it must be closed under all direct sums, kernels, co-kernels, and more generally just closed under arbitrary limits and co-limits. And finally, it must be closed under extensions. So let me briefly remind you of what extensions are. So if A and B are two abelian groups or condensed abelian groups or modules, whatever, then an extension is a short exact sequence. So you have A and B, and you have a new object E in the middle, and you want that to be short exact. In other words, F should be injective, G should be surjective. The image of F should be equal to the kernel of G. And so what we want is that if A and B are inside this category of complete modules, then every E that can be put inside such a short exact sequence should also be considered complete. Okay. So what are, now that we have this definition, what does that mean? Well, by a version of the adjoint functor theorem, the fact that this category is closed under all limits and co-limits, etc., is going to mean that there will be an adjoint functor to the inclusion. So the complete modules are a subcategory of the ordinary modules over R triangle, and there is an adjoint functor that tells you how to complete an ordinary module and end up with a module in this category of completed modules. And this means that we can also define a completed tensor product. So whenever you have two modules, you can just tensor them over R triangle and then pass through this completion functor. And so that gives you the tensor product over the analytic ring R. Okay, so how do you build an analytic ring? Because if you have to specify this subcategory and then check all those conditions, that might get a bit complicated. So one way to build an analytic ring is just to provide our triangle, and then for every S that is a continuous quotient of the Cantor set, we're just going to define R adjoint S. So our triangle adjoint S is going to be the free R module generated by S. And now we want R adjoint S, so that's going to be the free complete module generated by S. So we are going to define those, and then we build the entire category of complete modules by just taking direct sums, kernels, co-kernels, etc. of these free completions, because this subcategory mod R has to be closed under direct sums and limits and co-limits. So we just generate this category starting from the free completions RS. And then we need to check that these RS really behave as if they are freely generated. And this has to do with these extensions. So when do objects behave like they're freely generated? Well, certainly whenever you have a map from one of these continuous quotients of the Cantor set S to a module M, then it must extend uniquely to the freely generated object. And so we want this behavior whenever M is complete. So M is going to be one of these complete modules that we just generated. We built this category by taking all limits and co-limits, etc. And M is going to be one of those objects. Whenever we have a map from S to M, it needs to extend uniquely to a map from RS to M. But also, whenever you have an extension, then, well, if you map onto a freely generated object, then you want to have a splitting. And so if we claim that the RS behave as if they're freely generated, then they should also have this property. And more generally, there will be a condition for every I saying that this X group, classifying extensions in degree I, so this, for I equals 1, it will be these short exact sequences. And whenever I is larger than 1, these sequences will become longer. But we want all those sequences to be trivial in a suitable sense. In other words, we want these X groups to vanish for all I larger than 0. And okay, so that's the kind of thing that you need to check if you build your analytic ring using the recipe that I just described.
So maybe can I ask about the previous slide, with the free things?
This one?
Yeah. So because before you said that our triangle also has to be in this mod R inside, right? But then if you take if you take the free thing on one generator, it's not our triangle, it's different, or?
Okay. Okay, so I guess I missed maybe one condition. I guess you need to check that these objects behave as if they're freely generated, and maybe you should also check that R of a point is equal to our triangle.
Okay, so you do want this.
Yeah, I do want this, and I think it doesn't follow from this check. So
okay,
yeah, so that's a good point.
So my question was, to provide this free completion, which is like you're saying is some structure you have to some choice you have to make or something. You don't have any choice for finite sets, right? So funny things can only happen when you plug profinite.
Exactly.
Okay.
Right. So that's a good point. So whenever you have a finite set S, it's just going to be R triangle adjoint S, because it's going to be the direct sum indexed by S of R triangle of a point.
Okay, thanks.
Exactly. So the choices that you make here they're only interesting for infinite quotients S. That's right. Okay. So the easiest examples of analytic rings are just discrete rings. So you take a discrete ring R, you view it as a condensed ring, and you declare every module over R to be complete. And so you've just done nothing. And this is a way to view every discrete ring as an analytic ring. But it's not completely silly. I mean, the upshot of this means that you can play out all of commutative ring theory inside this world of analytic rings. And as a consequence, once you start doing geometry, schemes will be examples of the analytic spaces that are built from analytic rings. So it's a good thing that we have this example, even if it's trivial. So the next example is that of the solid analytic ring structure on the integers. So what we do here is we define Z adjoint S solid as the sort of a space of integer valued measures. So we have continuous functions from S to Z, and amongst those are the indicator functions for subsets of S. So you have some subset of S, and I suppose it should be a Clopen subset. And then you send everything that is in the subset to 1 and everything that is outside this subset to 0. And if the subset is closed and open, then this indicator function will be continuous. And so to every such indicator function, you have to assign an integer, which we think of as the measure of this Clopen subset. And then you have to assign to every continuous function such an integer valued measure in a linear way. So that's why you can think of this as a sort of space of integer valued measures. And the really crazy thing is that Noebeling proved that this space is a free abelian group. And that's pretty crazy. But as a consequence of the fact that this thing is free abelian, you can show that these spaces of integer valued measures really behave as if they're freely generated. Okay. So then we can try to play this game of measures also on the p-adic numbers. And so we have the p-adic numbers, and we're going to define a space of QP valued measures on S. It's going to be the union of all QP valued measures that have some sort of norm that is bounded by a real number C. So let's look at what exactly we mean by that. Well, we take continuous functions from S to QP and linearly map them to QP. And now we take those linear functions for which whenever you have a Clopen decomposition of S into n subsets that are closed and open, then you can look at the indicator functions again, and you apply mu to those indicator functions. So I'm abusing notation a bit. So whenever I write mu of u, I just mean mu applied to the indicator function of u. And so we could apply our linear function mu to those indicator functions, end up with something in QP, take the norm of that number, add up all those norms, and require that this is bounded. And the bound should be independent of the decomposition of S into Clopen subsets. Whenever that happens, we say that mu is a p-adically valued measure on S, and it belongs to this subset of measures. Okay. And so these are going to play the role of these freely generated objects. And the proof that they actually do behave as freely generated objects really relies on the non-Archimedean nature of the field of p-adic numbers. So we would also like to have the real numbers as an analytic ring. But of course, well, we probably can't apply exactly the same strategy as before with the p-adic numbers, because there the proof relied on the non-Archimedean nature of QP. So anyway, let's try the first attempt, and let's try to do the same thing. So we say, okay, we're going to define a space of real valued measures on S, and it's going to be all the candidates of measures that are actually bounded. So again, we take linear functionals on the space of continuous maps from S to R, and look at those linear functionals mu, for which for every Klopen decomposition, you look at where mu maps the indicator functions, take norms of those, and you want the sum of all those norms to be bounded by a constant C, independent of the Klopen decomposition. Okay. So that's a nice candidate for sort of a freely generated complete R module. But it doesn't work. So some computation involving the entropy function, where you look at, so that's this map, x goes to x log x. If you view that entropy function as a map from the L1 space of summable sequences to L2 modulo L1, so that's the square summable sequences modulo the summable sequences, then you can show that you get into trouble with this question about splitting extensions. So of course, you can turn this into a short exact sequence, and the short exact sequence shows that you have some extension, and this extension needed to have splitting behavior. And well, so you can define some convergent sequences in these spaces, and they don't have the required splitting behavior. So this space of convergent sequences, or the space of measures on the space that classifies convergent sequences is what I should say, does not behave freely generated. And this is in a, if we zoom out a bit, it's philosophically very much related to a 50-year-old theorem by Riebe, that you can have two Banach spaces and an extension of those two Banach spaces in the middle within the category of topological vector spaces. And this extension does not need to be a Banach space itself. And the reason has everything to do with norms. So on these Banach spaces, you have norms, and this extension in the middle, it will also have something like a norm, but it will be like an LP norm where P is less than 1. So you cannot, in the middle, you cannot put an LP norm where P is equal to 1. If you could, then it would be a Banach space, but you cannot do that in general. But that also suggests where to look for a solution. So instead of working with the classical norm on the real numbers, we're going to embrace the fact that we have to work with LP norms where P is less than 1. And if we do that, we might as well go quite general. So we're going to actually put in 2 layers. We're going to fix a number P between 0 and 1. P is allowed to be equal to 1, but it can't be 0. And now we're going to define a new space of measures. And it's sort of going to be like in analysis, you very often look at spaces of overconvergent functions. And measures are dual to functions. So here we want some sort of, I would like to call it under-convergent measures. So somehow these measures are going to be relative to LP prime norms, where P prime is allowed to vary anywhere between 0 and P. Okay. And then again, we take the union over all these bounds C. So the rest of the definition is going to look quite similar to what we've seen before. Again, we want to look at a sum of norms, and we want the sum of norms to be bounded for all Clopin decompositions by some bound that doesn't depend on the decomposition. But now we don't take ordinary norms. We're going to raise these norms to the power P prime. So we're going to take not exactly the LP prime norm, because then I guess maybe you would take you would take this entire sum and then raise that to the power 1 over P prime, but that, I mean, that just means that you maybe want to change the concept a bit. Doesn't matter. So what really matters is here we're taking additions, and here we're taking powers to the power P prime. And of course, those don't interact well algebraically. So there's really something different going on. And this is leading to interesting behavior. And yeah, so I stress again, P prime should stay strictly less than P. And then is allowed to vary. So these are maybe what we would want to call the space of underconvergent P-radon measures on S. And yeah, so it is what it is, but the good thing is that this second attempt is a lot more promising, and actually I can spoil the fact that this will turn out to be an analytic ring. But we do have to embrace non-convexity. So because we now are looking at these LP norms or LP prime norms for values of P less than 1, the unit balls are going to be highly non-convex, right? So this means that most of functional analysis doesn't apply to this situation, because very, very early on, you start restricting to objects inside the category of locally convex topological vector spaces. So here's a picture of what happens in the two-dimensional case when P is 0, you just get the axis cross. When P is a half, you get this orange shape, which is non-convex. When P is equal to 1, you get the square, which is just convex. And then for our values of P larger than 1, you get the usual circle for P is 2, and for P is infinity, you get this larger square. So yeah, I mean, this just means that we have to embrace non-convexity when working with these spaces. That also means that the proof is probably going to be tricky. Right. So the claim is that these spaces work, that they do behave freely generated. And what I want to do in the remainder of this talk is give you some ideas of the techniques that enter into the proof. So for that, we'll set up a little bit of notation. So we had this space M strictly less than P, and it was a union over all P prime less than P of these gadgets. And so I'm going to denote by MP prime of S sort of one of the terms in the big union over P prime. So it's going to be this union over all bound C of the P prime Radon measures less than with a bound less than C. And we need another definition. So I was telling you about this theorem by Riebe of that you can have two extensions of Banach spaces and two Banach spaces and an extension in the middle, and this extension wouldn't be a Banach space. But what is true is that it will be a P Banach space for all P less than 1. So what is a P Banach space? It's a topological vector space whose topology comes from a norm. So far, the definition is the same as Banach space, except that the norm isn't a usual norm, but it's a P norm. And so a P norm satisfies all the axioms of a usual norm, except the way it interacts with scalar multiplication is different. So normally, you would say if you multiply a vector by a scalar and take the norm, that's the same as taking the norm of the vector and multiplying by the absolute value of the scalar. But now we raise the absolute value of the scalar to the power P. And if P is less than 1, then again, this gives you a non-convex scaling behavior. And so, yeah, what Riebe's theorem is saying is this extension will be very, very close to a Banach space because it's going to be a P Banach space for its topology can be induced by a P norm for every P strictly less than 1. So you get very close to having an honest norm inducing the topology, but you can't be guaranteed to get there. In general, you'll have to be satisfied with the fact that it's only a P Banach space. Good. So then, to check that these spaces behave freely generated, we had to check, right? You have to check that these X groups vanish, and then you can do lots of categorical manipulations to the X groups that for which you need to do this check. And it boils down that on the right-hand side, you don't have to consider arbitrary objects from the category of modules that was generated. You only, in this case, need to check it for these P Banach spaces that we just defined. Okay, so we need to check that all higher X groups vanish between these spaces of P prime Radon measures and P Banach spaces. So I'm going to talk about the proof of this claim. Right, okay, so maybe I should say, so this theorem, the main theorem, this is what I would call the fundamental theorem of liquid vector spaces. And a liquid vector space is exactly going to be a complete vector space over this analytic ring of real numbers. But I want to give a little warning that the proof sketch that I'm going to give you will contain a few white lies. Otherwise, it isn't, I mean, it's just not possible to cover the full proof honestly within the time of one seminar talk. But anyway, this is all part of the liquid tensor experiment. So the proof has been computer verified. So anything I tell you today, even if it's wrong, a correct version is guaranteed to exist. This was done by a team of varying size, but roughly a dozen people. And I led this team together with Adam Topaz, and Peter Schulze was around all of the time answering all our questions whenever we got stuck and didn't understand some of the maths in the proof. Or, I mean, sometimes we found small mistakes and he would help us fix them. And so we checked the proof of this theorem in about 6 months. So yeah, so we need to compute those X groups. So let's think a little bit about how you do that usually. So to compute an X group, normally you would pick a resolution. Let's say we pick a resolution of A by projective objects. And then the X group would be the ith homology of the complex that you get by applying the functor of homing into B to this resolution. And so freely generated objects, like now I'm not talking about free complete objects, but I'm talking about honest, freely generated objects. Those are always going to be projective. Free implies projective. I'm just talking about the classical results in homological algebra. Okay, so it would be good if we have some sort of resolution that we can use to compute these X groups. And in the original proof by Schulze, he uses Brien-Deligne resolutions, which are resolutions of the following form. So whenever you have an abelian group or a condensed abelian group A, then there exists a resolution of the following form. So you take Z adjoint A, then you take Z adjoint A squared, and then you take Z adjoint A to some unspecified power. So beyond degree 2, this resolution becomes highly non-constructive. Like it's very inexplicit, and you can just prove that it exists. But computing what these numbers Ni are is pretty complicated. But so it has the following two properties. First of all, it's functorial in A. And secondly, so we have two addition maps. One addition map comes from just the usual addition on these groups, right? I mean, you take the freely generated group generated by A to the K, and well, that's a group. It's a freely generated group, so there is an addition map on that. On the other hand, this functoriality means that the map from A squared to A, the addition map, will also induce a map of complexes. And those two maps are not going to be the same because, well, unless A is trivial, I guess. No, that also then they won't be the same. Because Z adjoint something, that's a functor, but it's not an additive functor. So Z adjoint underline doesn't map sums of linear maps to the linear map of the, sorry, it doesn't map a sum of two linear maps to the sum of where it maps those two linear maps. It's not an additive functor. So we have two ways of getting an addition on these complexes. And so the claim is that, well, they'll never be the same, but in this case, they will be homotopic. So if you would map into the derived category, then they would become the same. Okay. But showing that these Brien-Deligne resolutions exist, that relies on a whole bunch of homotopy theory, especially something. Basically, you need to show that homotopy groups of spheres are finitely generated in order to use like a bunch of homotopy theory that will give you the existence of these resolutions. And so when I started the formalization project, I wasn't very excited about the idea of formalizing that existence proof and all the homotopy theory that you would need to get that proof. So I was thinking, I will just write down the statement that such a resolution exists with these properties, because these are the properties that we need. And then I'll just prove it by sorry. And when we're done with the complete liquid tensor experiment, everything will be checked by a computer, except that there will be one sorry left. And that one sorry is the fact that Brien-Deligne resolutions exist. And it's unfortunate, but we'll just have to live with it because it's impractical for the purposes of this project to completely verify the existence of Brien-Deligne resolutions. So I wrote down this statement that there are resolutions with these nice properties. And I started playing around a bit with it. And then at some point, I realized that, that there is a construction that looks very similar to these Brindlein resolutions, and it seemed to have the correct properties. And so I started discussing this with Schulze, and so at some point we realized that this construction wasn't new, but I'd actually stumbled upon something known as MacLane's Q construction, and it's extremely explicit. So it starts out exactly the same as Brindlein resolutions. You take A, you take Z adjoint A, you take Z adjoint A squared, and then you just take Z adjoint A to the power 4, A to the power 8, and in general, in degree I, you take Z adjoint A to the power 2 to the power I. And so it's extremely easy to write down this construction. And then you can also show that it is functorial. I mean, that's even easier again. And it also has this additivity condition or additivity property that because of functoriality, you can plug the addition map on A into this construction and it gives you an addition map on the complexes, but also all these terms in the complex are groups themselves and come with their own addition maps. And those are going to be homotopic, those two addition maps. So that's good. The bad thing is, it is not a resolution. So exactness fails almost immediately. Like over here, we still have exactness. Over here, it breaks. But, so you cannot use it to compute arbitrary X groups. But if you want to show that X groups are equal to 0, then together with Schulze, I showed that actually you can use this complex. So it's not a resolution, it's a complex, but you can use this complex if you want to compute that X groups are equal to 0. And so that's what we used. And this lemma, this claim that it's good enough for showing that X groups are 0, I mean, I would say it's not completely straightforward, but it's certainly something that you can cover as soon as you've set up the whole terminology of X groups, etc. So it's basic homological algebra. Okay, so that's one thing that we can use. And wait, I'm confused. I thought there was another slide after this section. Okay, so it seems, okay, that's what I wanted to say about how we're going to compute these X groups. So then, now I want to say something about normed homological algebra. And so we have these spaces of P prime Radon measures bounded by C, and this is still an enormous amount of notation, so we're just going to abbreviate it to M at most C. Good. And we'll just write M for the union of all those balls of radius C. So this is the entire space of P prime Radon measures, and it's a union of balls of radius C. And then we had to compute X groups between M and V. So we apply this MacLane Q construction, and so we get a complex with terms of type Z M to the K of that shape. We apply the functor hom into V to that complex, and we end up with things like this. Well, so that is just like we're mapping out of a freely generated object. So that's just going to be the same thing as maps from MK to V, but not just arbitrary maps. They have to be continuous maps because we're in the category of condensed abelian groups, where, well, that's basically the definition. If you treat a p-Banach space as a condensed set, you look at continuous maps into V. Right, so in the end, we have a complex built out of taking continuous maps into V. And so we are also going to abbreviate this a little bit, and we're just going to write V applied to M to the K. Okay. So the goal is now to show exactness in degree I of this complex. And in degree I, we have this m to the power 2 to the I because of this MacLane-Q construction. Good. So if we show exactness, even though we started with something that wasn't a resolution, because of this little lemma, if we show exactness here, then we know that these X groups are equal to 0. And now we're going to do this is one of the white lies. We're going to pretend the balls of radius C are compact, but M itself is not, but we're just going to pretend that it is compact, because that will mean that this space of continuous maps from M to the K into V carries a sup norm. And like I said, it's really those balls of radius C that are actually compact. And so really, we should be looking at restrictions to the ball of radius C, look at the norm of that. This gives us a whole family of norms and work with this family of norms at all times. But I'm going to simplify the presentation and just work with one norm and pretend that all of M is a compact space. Okay. So now we're going to show, we want to show that that complex is exact, but that's really hard. So what we're going to do instead is prove something that is even stronger. We are going to make a stronger claim, namely that it's normed exact. I'm going to explain what that means in a minute. And the nice thing is, okay, this is a stronger claim, so it might be even harder. But the good thing is, it means that we can apply some induction procedure, and then the induction hypothesis will also be stronger. And that's good. So that's what we're going to use. Okay, right. So normed exactness will imply exactness. So to do that, I want to tell you one approach, which I've been working on together with Reid Barton, where we use a bit of logic to organize this whole setup of normed exactness, normed homological algebra, and hopefully simplify the presentation, or at least motivate how it comes into being. And as we'll see, it also provides a way to take all sorts of results from ordinary homological algebra and immediately get translated results about normed exactness and normed homological algebra. So anyway, we're going to work in a fragment of logic that is called regular logic. What this means basically is just whenever you have two formulas, you can take AND of the two formulas, and you can have only one implication within a formula. So you can have formula implies another formula, but you cannot have further implication symbols. And you can only have for alls on the left of an implication, and you can only have existentials on the right. So it's a very restricted subset of logic. But it turns out that this is exactly what you need when you're dealing with exactness. As we'll look at the definition of exactness in a moment to remind you, and you'll see that it is a sentence in regular logic. And so whenever we have variables in our formulas, we're going to interpret them as points in a metric space. And formulas themselves are going to be interpreted as real valued functions on these metric spaces. Okay, so that's all a bit vague, maybe, if you don't normally work with logic. So, but let's just look at a translation table. So we're going to have a formula, and let's say we just have the formula true. This is going to be mapped to the constant function 0. And so the way you should think of this is these functions on metric spaces, they're going to be some sort of landscapes. And the rivers of the landscape, so the points where the height is 0, that is where the formula really was true. So, okay, so what I should say is the height of these functions measures how false our formula is. So we're doing a version of logic where we now have truth values in the real numbers. That's why so if we have a 1-point space, then formulas are mapped to a real valued function on the 1-point space, and the truth values will be real numbers. They'll actually be positive real numbers or non-negative. 0 means that the formula was absolutely not false. So, right, the function measures how false the formula is. If it's mapped to 0, it's absolutely not false. If it's mapped to infinity, then it's very, very non-false. So it's very, very false. So it's actually false. And the stuff in between, I mean, doesn't have an interpretation in classical binary logic, but, well, it's just going to be some value. And so the next example should really motivate that. So now we have a space with 2 points, x and y, right? The formula x equals y is going to be mapped to the function on the product space x cross x that takes the real value, the distance between x and y. And so it's going to be a landscape with a river exactly along the diagonal. Whenever x equals y, so the diagonal in x cross x, then the distance is 0. And so that's exactly where x equals y is very true. Just away from the diagonal, x equals y is a little bit false, mostly true. And so the distance between x equals y takes a small value. And if you move farther away from the diagonal, the distance will increase. And so the falsitude of this formula also increases. Okay, so we interpret equality as the distance between 2 points in a metric space. Whenever we have 2 formulas and we take their conjunction, then we could take the landscape of a conjunction is going to be the landscape of the left-hand side plus the landscape of the right-hand side. Okay, so whenever you do implications, so here, this implication symbol, like I said, you're only allowed to have 1 implication. And that is also for the following reason. Because the interpretation of this is no longer actually going to be a landscape. It's not a function on a metric space, but you take the left-hand side and the right-hand side. Those are going to be 2 landscapes, and we're claiming that one of them is less than the other. So this formula is not interpreted by a landscape, despite what I said a moment ago. And that's also why you can have only 1 implication symbol. But so this is going to be interpreted by an honest claim. It says there exists a positive constant such that the landscape that was on the right-hand side of the implication is less than k times the landscape corresponding to the left-hand side. Okay. Then we have for all, and that's just, well, that's just what it is, and existentials are interpreted by Infima. So now let's move on to the example that we really care about, namely exactness. Okay, so exactness says for all b in capital B, if the differential maps b to 0, then this implies that there exists a little a such that the differential maps a to b. Right, so we have exactly 1 implication symbol, we have a for all on the left, and we have an existential on the right. And so now we can, and we have some equality signs, etc. Okay, I didn't tell you maybe how to interpret 0, but well, it's going to be a special point in the metric space, and the metric space is going to be a normed vector space, say. Okay, so then we can run this translation table, and the output is what we will call normed exactness. And so we had this implication. The implication meant there is going to be a capital K such that the interpretation of the right-hand side is going to be less than the interpretation of the left-hand side. Okay. The right-hand side had this existential, and dA equals B. So we get the infimum over all A of the distance between dA and B. In other words, the norm of B minus dA, because our metric is coming from a norm. And on the left-hand side, we just have this equality, dB equals 0, and that's just going to be the norm of dB. So yeah, I hope this explains how this translation table means that you can translate sentences in, well, what is called regular logic into some sentences involving metrics or norms, etc. And so this is the definition of normed exactness that basically appears in the proof that Schulze wrote. Good. And so what is the informal meaning? It means that, well, whenever you start with an element B in the middle term, then you map it to C, that's going to be dB, and the norm of dB places a bound on how hard it is to find a pre-image for B. So if dB is very small, then you can find an element little a that is mapped to something really close to B. So it's a pretty good pre-image. It's not on the nose a pre-image maybe, but it's really good. If the norm of dB is very large, well then it might be really hard to find a good pre-image, and you'll have to be satisfied with a very bad pre-image. On the other hand, we see that this implies ordinary exactness, because if d of B actually is equal to 0, well, then that means that here the right-hand side is 0. And so it means that this infimum has to be 0. So that means that we can find a sequence of a's, of little a's, that approximates a pre-image of B. And so if our normed vector spaces are actually complete, well, then we can find a converging sequence and take the limit point, and that limit point will actually be an honest pre-image of B. Okay. So that shows that normed exactness is actually a stronger concept in the complete setting than ordinary exactness. Okay, and so this Lipschitz logic gives an automatic way not just to translate formulas, but also to translate proofs. And so we can take the statement of the snake lemma, translate the statement of the snake lemma into a statement about normed exactness, and we'll automatically know that that statement about normed exactness is correct. And the reason for this is a pretty high-powered result. It's very closely related to Deligne's completeness theorem for coherent topoi. So there is also a completeness theorem for regular logic. And that means that whatever you used in the proof of the snake lemma, classically, it really doesn't matter. Because there is a proof, there is also a proof that only uses regular logic. That is what this completeness theorem says. And so we know that there exists a proof of using only regular logic. We can push that through the translation table of Lipschitz logic, and that will give us a proof, or at least we will know that there exists a proof of the statement about normed exactness. And so we automatically get for free a normed exact version of the snake lemma, of the long exact sequence of homology groups, of spectral sequence arguments in double complexes, etc., etc. Okay. So let me see. When am I supposed to stop?
maybe like 5 minutes ago.
Oh,
5 minutes ago.
man,
Something,
I'm sorry. Okay, so let me use like 1 more minute to wrap up. Okay, I'm sorry for going over time. So okay, we did lots of manipulations and lots of homological algebra using this Lipschitz logic. And then in the end, there is one key problem that remains. Namely, we need to show that the map from M to the N to M is surjective. And here we again need to think about these. It has to be surjective in a way that is compatible with these balls of radius C. So you cannot just project onto the first vector. Okay, and so this is the precise statement. And so that is another hurdle that you need to take. And I can tell you a bit more about that, but I just wanted to say, so once you've done all this homological algebra, there's one more hurdle that you need to take. And this is really where the non-convexity throws another wrench into the whole theory. So you have to buckle down and use some results about polyhedral lattices and sort of convex combinatorics to show that you can make this work. So I had some more slides on that, but let's stop here. So thanks a lot for your attention, and sorry for going over time.
Yeah, thank you very much for the nice talk. So is there any question from the audience? Okay, so maybe I have 2 questions. One is very naive, I think. So I don't doubt Scholze or anyone, but so I guess to define this analytic ring structure on R, we did make some choice. So is there a reason why this is the right analytic ring structure on R? Like, are there some natural characterizations of R as an analytic ring, or why do we know?
Yeah. So that's certainly a very good question. So why is it the correct analytic ring structure? So for this analytic ring structure, you can show that Banach spaces and Frechet spaces and all those spaces are complete. And not only that, so this is going to mean that things like the ring of smooth functions on a manifold or on some disk or subset in an open subset in a manifold is going to be a liquid vector space, so a complete space over this analytic ring, and also holomorphic functions in the complex analytic setting. But also their tensor products are correct. So if you take 2 disks and you take holomorphic functions on them, then the tensor product computed in this liquid setting is going to be the space of the liquid vector space of functions on the product of the 2 disks. And so that is the behavior that you want. So that justifies why this is, I think that is one of the main reasons to say that this is the correct analytic ring structure on the reals.
I see, thanks.
Mm-hmm.
Okay, so some other question.
Yeah. Hi, so there was a remark quite early in the talk about being able to mix different flavors of geometry. Say, for example, smooth manifolds and algebraic varieties over C. Let's take that example.
Yes.
Are there kind of honest examples of that, other than taking a direct product or something? Maybe like I take a smooth variety X, I take its product with an interval, I take another copy of X and take its product with an interval, and I glue in some non-obvious way, and I get like a smooth circle bundle over a algebraic variety, something like that. Are any examples like this known that really mix the 2 things?
So I think the answer is not yet.
Not yet. Okay.
Yeah.
I mean, typically physicists do tend to work with things like that. I mean, they consider field theories over, one direction is holomorphic and one direction is smooth and so on. And it would be very interesting to have this in mathematics.
Okay. I know very little about mathematical physics, but so that's certainly an interesting remark. And I can certainly imagine that maybe being in a place where you want to, I mean, you could of course already mix holomorphic and smooth in the classical picture, because holomorphic is just a subcategory of smooth.
Sure, yeah.
So that's maybe not really directly a place where this adds value, but what is nice is you can start looking at spaces. So you can look at the space of all norms that you can put on Z, the integers, and this is something called the Berkovich spectrum of the integers, basically. And I think people are constructing families of spaces that somehow, if you then take the fiber, like over this Berkovich spectrum, if you take the fiber over the real numbers, you get some sort of real manifold. If you take a fiber over a p-adic norm, you get a p-adic like Berkovich space or adic space or something like that. So it gives you a way of building families that maybe interpolate between Archimedean and non-Archimedean behaviors as fibered over this Berkovich spectrum of the integers. So that's maybe not exactly in the direction that you were thinking, but I think it is an example of how people are starting to mix Archimedean and non-Archimedean geometry within one big framework.
Thanks.
Mm-hmm.
All right. So is there any other question? Okay, so maybe I'll quickly ask this other thing, which every time I hear this quasi-coherent shifts on complex geometry, I mean, of course I agree, it's nice, but so is there any really new results that have been proven using this that were not proved? I mean, we didn't have a proof before, and now we can prove them with this, like some conjectures or something like this?
So I'm not aware of new results that are proven this way, but it does mean that like once you've set up this category and the six-functor formalism for it, then things like Serre duality and Riemann-Roch-like theorems and finiteness of coherent cohomology, all those sort of results just roll out of the usual six-functor formalism proofs. And so those proofs used to be extremely hard and use things like Hodge theory, etc. And yeah, so those proofs are simplified a lot.
I see. Okay.
And I should maybe point out that sort of a recent development is that so Clausen and Schulze are teaching a course right now on analytic stacks, and in that they present a new type of analytic ring. So I've been talking about these liquid vector spaces and the liquid analytic ring structure, and that is what you really need if you're doing smooth manifolds, differential geometry kind of stuff. If you only care about holomorphic, so complex analytic stuff, then you can also use the so-called gaseous analytic ring structure, which is a lot easier to construct. So here I've been talking about this proof, and I showed you some ingredients using this Lipschitz logic, etc. And there are many hurdles along the way. But showing that you have this gaseous analytic ring structure is really much, much easier. And that is good enough if you're interested in the complex analytic setting. And so I think altogether, that really constitutes it doesn't just shift the complexity from, oh, we were doing Serre duality and we needed Hodge theory, and now we're doing this proof using liquid vector spaces, but it relies on this really complicated proof in the liquid tensor experiment. Because now you have this other approach using the gaseous analytic ring structure, which doesn't require an enormously complex proof like the liquid tensor experiment.
Mm-hmm.
So,
I see.
Yeah.
Mm-hmm. I see. Thanks. All right. Any other questions or remarks? So let's thank the speaker again. Thank you.